So, hello and welcome. And thank you for joining me on this Friday. Today's only announcement is that you have homework due Sunday, and it's split up into two pieces. But I do want to mention that one of the sections is on this applied optimization. So I recommend you give yourself a little time to think about a few of the problems. So don't save it all till Sunday if you can help it. Um, but yeah, other than that, today we're going to be covering section 3.9. But before we get into that, does anybody have any questions or comments about how the class is going? Alrighty, so section 3.9 is sort of a beginning of sort of the second segment of calculus. So up till now, we have spent a long time, basically everything since the beginning of the class, really what we were trying to do is we were studying this concept of the derivative and some applications of it, right? If I can spell it correctly. Studying the derivative of a function, which we usually called f prime of x or df dx. When do I think test grades will be in? Hopefully by the end of weekend, but I can't guarantee that. But that's when I'm hoping to do the majority of them. Yeah, so we spent a long time thinking about the derivative, which was, when we asked the question, what was the rate of change of something? Now we're going to switch gears and consider sort of the opposite question. So can we undo this operation? So that means, if we're now given if we only know the derivative, is it possible to recover the original function? So can we undo the derivative is essentially what we're going to start talking about now. And the answer to this is going to turn out is that yes, sort of. It'll turn out that we can find f of x, but we're not going to be able to find f of x exactly. We're only going to be able to find it up to a constant. Okay. So again, sorry about the beeping. So again, what we're trying to do is we're asking, if we're given the derivative, how do we go backwards and find the original function? And we did briefly have a theorem about this that I want to remind you of, because it's kind of the basis for everything here. We had this theorem when we talked about the mean value theorem that said that if you have two derivatives that are equal, on an interval, say a to b. So if you have two functions whose derivatives are equal, then you can say that, well, the functions themselves don't have to be exactly equal, But what they do have to be is they have to be equal up to a constant. So one could be shifted up or down by the other, right? For some constant, some particular number. And this is still on this same interval. And so really what this is saying, let's think about this is, if I take a, maybe I shouldn't go too quickly. So if I had something like, if I knew the derivative, if this was all I knew, let me put it in the middle. If I knew this was the derivative, and we were asking the question, what is the original function f? Well, we could start, guessing what the original function is. So we might guess what f of x itself is. And if we try x cubed, we would see that if we take the derivative, this would become 3x squared. But there are other functions that work as well, right? If I took g of x to be x cubed plus, say, 7, and I took the derivative of that, this is also 3x squared. So this is really what the function was saying is, I have two functions, f and g, whose derivatives are equal, but they don't have to be the same, but they do differ by just a constant. And that's really the only way that can happen, is what we're saying is, if two derivatives are equal, then the functions have to be equal up to a constant. And the basic idea is, if you look at the two graphs, x cubed just looks like that. And like x cubed plus 7 might look like, and these both have the same derivative, right? Because if you choose any particular point, let's not use green. If I choose a particular x value on both of them, try to pick the same one on both, then shifting it up or down doesn't really change the tangent line, right? They should have the same slope even if it was shifted up or down. Making it worse. Okay. So yeah, shifting a graph up or down doesn't change its derivative, is the point. Okay. And so we give this kind of process a name. What we're doing now is instead of taking the derivative, we're taking the antiderivative. So this is the definition we're working with today, is that we say a function f of x is an antiderivative of little f, so lowercase f, on the interval a to b if, so what you have to check is if when you take the derivative, you get back f. So it's sort of saying like normally we would say, you start with a function, you take its derivative, and you would get f prime, right? So now instead of writing f prime, we're writing f of x, And we're thinking of it backwards. So we're starting with little f, and we're saying go backwards and find the capital F. And this is called the antiderivative. It's the reverse procedure. Okay, and later we'll have a symbol for that. It'll be the integral symbol. But that's going to take a few sections to get to. But it's yeah. So an antiderivative is something whose derivative is what you start with. Okay, so let's see a simple example of that. Like we just kind of did this. So let's find two different antiderivatives of x squared. Okay. So we want something that when we take its derivative, so we're saying like the derivative of what is x squared. And whatever goes in this slot is our antiderivative. So if you think about it, because we want to end up with an x squared, we have to start with, x cubed and then possibly times something, right? So we might first try x cubed, but if I did this, then I would end up with a 3 here, right? So to fix that, I put an extra, a third here, and then these go away. Okay, so f of x is an antiderivative of x squared. Okay. But the question asked us to find two of these. And right, so whenever you're doing antiderivatives, you want to double check that, when you take the derivative of your thing, you better get back to here, right? Because the definition was if you take the derivative of the capital one, you get the lowercase one. So I kind of call them big F and little f. Right, so the derivative of big F is indeed little f. And now if we want to find another one, so maybe we call this one f1 and this one will be f2. If I take the same thing and then I just add a constant to it like 735, this one is also an antiderivative, right? Because if I take the derivative, the derivative of the constant just goes away. Okay, so nothing super complicated there. And based on what we were talking about before, what we can say is that let me write it like this. All antiderivatives, so every single one, because there are more than one possibility here is the point. So we can actually describe all possible antiderivatives. They're always, if you choose one particular antiderivative and then just add a constant to it, that's another antiderivative, and it turns out that that's all that can ever happen. So every single antiderivative is of the form a third x cubed plus some constant. The constant could be 735, or it could be 2, or it could be 3. There's one for each possible constant. So it can be important to remember that there are an infinite number of antiderivatives. So that means if there is one, there's an infinite number. Derivatives. right? And they all are just, you find one antiderivative, like we did up here, and then you can shift it up or down, because shifting up or down doesn't change the derivative. And that's the adding the constant part. Okay. And so the way we're going to phrase this is that we're going to call this the most general antiderivative. That's just going to be the term we use. To describe all antiderivatives. So whenever we say the words most general antiderivative, what that really means is it stands for not just one particular function, but really, you could plug in any c value. So you get one for each c value. And so it stands for the collection of all antiderivatives. Okay. So sometimes we'll only care about a particular one, but if we don't know which particular antiderivative we want, we just kind of write them all down by writing down the most general antiderivative. Okay, so the idea is to find the most general antiderivative. All you do so what you do is you find one antiderivative. So that's, you always have to first find at least one. Then you just add the plus c. Okay, so the idea is you just find one and then you add plus c, and that gives you all of them. So it's actually not too bad, though it turns out taking antiderivatives is usually a bit harder in general. And so we're not going to get into all the ways to calculate the antiderivatives today. We're just going to stick with some simple ones today, and later, once we talk more about the integral, we'll have a little bit more techniques to compute them, to compute more complicated ones. So here, the ones we're going to start with today so I'm going to write it as a table. We're just going to do like 3 of them. But little f will be the original, and capital F will be the antiderivative. So this is sort of a convention. So the convention is the antiderivative, and it's not always the case, but it's quite common that if you take the antiderivative of a lowercase, you call it an uppercase. So like if you're taking the antiderivative of a lowercase f, you get the capital F. With the same letter. Right, so you would go like little f to capital F, or little g, take the antiderivative, and its antiderivative we would probably call capital G. It's just something that helps us distinguish which is which. And you can do this for just about any letter. Okay, so here that's why we have this convention. Okay, so now if you think about it, if I take the antiderivative of x to a power, you would want something that when you take its derivative, you get x to the n. And so that means you have to start with one higher power. So its antiderivative will have one higher power. And then what it turns out you have to do is, you have to divide by that new power. So this is sort of the inverse power rule. And you have to be a little careful whenever you're dividing, right? You don't want to divide by 0. So this only works when n is not -1. Okay, because if n is -1, there's actually a different formula. It's a natural log, but we're not going to cover that in this class. You can look it up if you'd like, or take Calc 2. The other two we're going to stick to today are just sine and cosine. So what are the antiderivatives of sine and cosine? Well, the antiderivative of sine would be saying we want something whose derivative is sine. So we might at first guess cosine, but we know that the derivative of cosine would be negative sine. So we need to put an extra negative in here to fix it. For cosine, we might guess first sine, and then we check, like, is the derivative of sine cosine, and it is. So that one's just fine. So these are things that are worth memorizing, I would say. And there's a few other ones. Another thing I can mention is if you look at this top one, compare this to the power rule for derivatives, because this is supposed to be somehow the opposite of the power rule, right? So the power rule said that the derivative of x to the n was n x to the n minus 1. So you could think of that as saying, bring down the power, then subtract 1 from the exponent. So if you're going to do that backwards, so instead of subtracting 1 from the exponent, you do it in the reverse order and you do everything backwards. So instead of subtracting 1, you add 1 to the power. And then instead of multiplying, you divide by the thing that you did by the new thing, right? Because before it was bring power down, then subtract 1. So in reverse, you add 1 to the power, then you divide, right? Because division is the opposite of multiplication. It's the thing that undoes it. But anyways, it's just something that this one's, these are definitely worth memorizing. We're going to be doing a lot of these. Okay. So let's do a few examples now. Okay, so we're just going to go and compute some most general antiderivatives. So again, this is a thing where we're computing the most general antiderivative. And it works very similar to derivatives. So we'll learn later that there's some rules, but it turns out, this is, for us right now, it's a little bit of a guess and check game. Like, we just want to figure out something that has this thing as its derivative. Okay, so it turns out you can just do that term by term. And so if we apply, this inverse power rule, it would say you add 1 to the power, and then you divide by the new power. And you do that for all the x to the power terms. And if you have a constant, well, really what you can think of that is like, x to the 0 is really 1. So there's really like a hidden x to the 0. So really you can think of that as being Or you could just ask yourself, what has derivative 5? And you would guess 5x. But really, you can also think about it as this rule we learned. And okay, so this is the basic idea. If this thing that we wrote down will be an antiderivative if you check it, so we would think that the most general antiderivative would be 3 over 3x cubed plus 1/10, or sorry, 1/11th, x to the 11th plus 5x, and then we have to tack on always plus c here to make sure we get all possible antiderivatives. Okay, and so yeah, it's always worth checking, at least when it's an easy thing to do, is just, if you take this derivative, so you could simplify this out to just like that. If when you take the derivative, do you get back what you started with? And indeed you do, right? You'll get 3x squared. The 11s will cancel. You'll get x to the 10th. Derivative of 5x is 5. Derivative of c is 0. Right? So you can just do these things term by term as long as they're added together. If they're multiplied, it doesn't work the same way. It's just like, you can't take the derivative like that either, right? You have to use the product rule. And okay, so any questions so far? So for this one, we can also just take the antiderivative of each term. And so we learned before that the antiderivative of cosine is just sine. The number sits there just like it does for derivatives. And we'll learn these rules in particular, like I'll lay them out very specifically in a few more sections. And for this term, it's just like derivatives. It's kind of worth writing this as a power so we can use the inverse power rule. So this, we would add 1 to it. And then we would divide by that new power. Okay, so we would think that g of t, right? We write the capital for the antiderivative. At least that's the convention. It's going to be 3 sine of t minus, so this bottom is a half, so that'll flip up to be a 2. And then this will be t to the 1/2. And then we tack on our plus c. Right? And if you're ever unsure, you should just go back and check. Like if you take the derivative here, do you get back to what you started with? Then you will here, right? You'll get 3 cosine. The 2 will cancel, and then you'll get the negative half power for the second term. Derivative of c will go to 0. Okay. So, things can get a lot harder. And we'll talk about some ways to handle harder things later. But integration actually turns out to be a much harder thing to actually compute in general than derivatives. Derivatives are just kind of mechanical. You have the rules that you apply. You have to be a little bit more creative for some antiderivatives. So for example, for this one, we said before that the antiderivative of sine was negative cosine. So we would probably guess that there's going to be something involving a negative cosine. But now you have to start thinking about the chain rule, right? So if I was to take the derivative of this, what would I get? I would get minus 3 cosine of 3 theta. So that's, minus sine. Right, the derivative of cosine is negative sine of 3 theta. And so if you work this out, this would be 3 sine theta. 3 sine 3 theta. But that's not quite what we want, right? We want just sine of 3 theta, so that means we're off by a factor of 3. So we can fix that by putting in an extra 1/3. And that will get rid of these extra 3's everywhere, right? Okay, so we would expect that the antiderivative of the first one, so we kind of had to undo the chain rule here. And the second term we can think of as being theta to the 1/2 power. So we might think that h of theta is minus 1/3 cosine of 3 theta minus theta to the 1/2 plus 1 over a half plus 1, which is, I'll just write it, and then we tack on plus c. So if we simplify that, that's what? That's, so a half plus 1 is 3/2, so that'll be a minus 2/3 theta to the 3/2 plus c. Okay. So like I was saying, like sometimes it's a little bit of just a guess and check, at least for us right now, especially if there's something a little bit more complicated than just sines, cosines, or x to the powers. But we're not going to get that complicated yet, at least. Okay, and one more of these. So here's an example where it's even more difficult, I would say. So we look at this and we say, well, I don't really know what function has this as its derivative. But one thing we can notice is, when you're thinking about taking derivatives, we only have a certain number of rules, and we think about like which of the rules, if you were to use them, would end up with something like this. So it's probably not going to be like a product rule. The thing it looks most similar to would be the result of a quotient rule, right? So let's imagine that we're using the quotient rule to do this. Right, so remember, right, f, if you start with a fraction, when you take its derivative, it'll be over g squared. And so sort of the easiest thing I would identify is I would identify the g squared with this denominator, right? Because it's something squared and it's in the denominator. So that would mean that my g is probably just the y squared plus 1. So we might at first guess that r is something that we don't know over y squared plus 1. And we want to see, well, what would I have to put in on the top so that when I take its derivative, I get little r? Right, so what I would just imagine is like if you had to actually do the quotient rule here, what would you get? So what would r prime be? Well, it would be the derivative of this thing we don't know what to put there yet times the bottom times, well, our unknown thing times the derivative of the bottom over the bottom squared. So you see we have the bottoms matching up, right? So we see the y squared and 1, y squared plus 1 squared matches up with this original. And so what we need now is we need this top to match this to just be y. So what could we choose for question mark? If we were, once you get the hang of this, you would probably just give this a name. Like you would call this like, I don't know, f. We typically don't like calling things question mark, but it's the same idea. So you might just give it some name f, but it's really, we're asking like, what is f? Yeah, what should I choose for f? So let's do a little simplification first. Let's see. This would be f prime times y squared plus 1. Let's make it clear that we're going to have it like this. And then we would have f times 2y. And so okay. So we want this part to be equal to y, right? And I mean, you could actually go through solving this, but it's not that easy to think about in terms of solving. It's you just kind of want to guess, like, what is something simple you could try here that will give you what you want. And so what I see is in the second term, I have my y, but it has a 2 and an f. So that means in order to avoid having a y squared, maybe we just choose f to be like a constant or a number or something, like 0 or 1 or some other number. So maybe we try, we're just guessing and checking. Like maybe we choose, like what would happen if f was 1? So if f was 1, then the derivative of f would be 0. So that first term just goes away. And you'd be left with minus 2y. So that's getting a lot closer, right? That's almost exactly what we want, except for the part that's wrong with it is we don't like this minus 2. So to fix that, what if we change our guess to be, instead of f being 1, to get rid of the minus 2, we're going to instead take a minus to cancel the minus and a dividing by 2 to cancel the 2 out. Then what you'll end up with here is minus a half times 2y. And so yeah, now you end up with exactly what you wanted. Okay. Okay, so yeah, this one was a lot more difficult, but what we reasoned out in the end was that capital R of y should be, so our guess was where? So this was our guess, right? And f we decided was minus a half. And then we add a plus c at the end. Okay. So, I mean, the main point of this problem was, it can be difficult to do this without any sort of procedure to guide you, right? And later we're going to start learning some procedure. But yeah, so yeah, that was kind of how we think about just doing some basic antiderivatives. There's some very simple rules we can memorize. And basically, they're basically just, if you know how to take the derivatives of something, then whatever's on, like another example is like, what's the antiderivative of cosecant squared? Well, we know that if we take the derivative of cotangent, we get negative cosecant. So you can read it backwards. It's like if you know the derivative rules, they give you the antiderivative rules as well. You just read them backwards. Okay. So any questions about this most general antiderivative business? Okay, so yeah, before we do this, let me tell you what this is about. So one of the places that this comes up quite a bit is a lot of times in applications, you run into situations where what you really want to solve is a problem that looks like this. So these are called initial value problems. And an initial value problem so this quite frequently gets shorthanded as IVP. So they're most normally written as you have a derivative is given to be something. Like you're given the derivative of the function. So the derivative is some function f of x. And you're given a second piece of information. So you know that the derivative is some equation, and you know one point on the function. Let's write it as like this, x naught. Okay, so you're given the derivative and a single point, and what you would like to know is the antiderivative. But we said there's many antiderivatives, right? And here's where we commonly kind of break the convention when we're not using any capital numbers. So we're trying to find the one single antiderivative that satisfies both these things. So we're only looking for one here. So we're not looking for the most general one, we're just looking for one in particular. These. Okay. And so yeah, so that's kind of the definition. And it's easiest to understand sort of what these are by doing examples, because it's a pretty simple procedure. So let's just look at a few of them. So here we're just going to go through a few of them. So in the first one, we're given that the derivative of y prime, is 1 plus x squared. And we're given also that, this means the x value is 1 and the y value is 2, right? Because y of x, you plugged x equals 1 in and you got 2 out, right? So it means if the derivative is this and the function goes through this point, what antiderivative makes that work? So the idea is we want to solve for y. Okay, so there's basically just two steps. Number one is you do what we were doing before, and you find the most general antiderivative of y prime. So we want to figure out which function has as its derivative 1 plus x squared. And here that would be, so the antiderivative of 1, well, what has derivative 1? That would just be x. So y will be x. Antiderivative of x will be, well, that's kind of like x to the first, right? And so we increase its power by 1. to a squared, and we divide by the new power. Then for x squared, we increase its power by 1, and then we divide by the new power. And then to make it the most general is we have this plus c. So this is all possible antiderivatives. Our goal is to figure out which of these antiderivatives goes through this point, 1, 2. So that's the second step, is once you've found all the antiderivatives, you use so that second piece of information is usually called the initial value, which is why these are called like initial value problems. Because a lot of times, like when you're doing an application, you know the starting, how something started. So like at time 1 or time 0. And you use that to solve for C, to find which particular constant makes this work. And so here, we said that y of 1, which is 2, well, we plug 1 in because x was 1, right? So we plug 1 in, so it'd be 1 plus a half plus a third plus c. So, really we end up with this equation. We plugged 2 in for y, and we plugged 1 in for x, and then we solve for c. So c will be 1 minus a half minus a third. And let's see, what is that? If we write that all in terms of thirds, that would be, or sixths, I guess. 6 minus 3 minus minus 2. So that's c is 1 sixth. Let's see, can I move this down? Yeah, so we found that c is going to be a sixth. And basically what we do is then our answer is the y we first found, but now we use our particular c. So the answer is y is x plus x squared over 2 plus x cubed over 3 plus 1 over 6. So this is the one particular antiderivative that satisfies both pieces of information. If you take its derivative, you'll end up with 1 plus x squared. And if you plug in 1, you'll get y equals 2. Okay? So that's called an initial value problem. Okay, let's try another one. Unless there's questions. Okay, so again, we would start here by finding the antiderivative, the most general one. But here we have this pesky little pi like inside the cosine, right? So we have to do a little bit of guess and check, right? So y of t here, well, we saw before that the antiderivative of cosine is sine. So we might first guess sine of pi t. But if we were to take this derivative, this would give us pi times cosine of pi t. Right, where the pi came from the chain rule, the extra pi. And so we don't want that extra pi because we want just cosine of pi t. So that means we need to cancel it out with an extra 1 over pi. And now when I take the derivative of 1 over pi sine of pi t, I do indeed just get cosine of pi t. And then a similar thing happens in the second term. So the antiderivative of sine is negative cosine, so that switches it to a plus. And then because of this pi inside, we have to correct it by a 1 over pi. And then to make it the most general one, so that we get all of them, we have to add our plus c. Okay, so this would be the most general antiderivative. Second step would be to plug in, so y of 0 means we're plugging t equals 0 in, that better be 1. So that'll be 1 over pi sine of pi times 0 cosine of pi times 0 plus c. And so if we evaluate all that, so sine of 0 is just 0, cosine of 0 is 1, and then we solve for c. So c is 1 minus 1 over pi. So our final answer is then we plug that into the original y, so y of t is 1 over pi sine of pi t so we copy all this part, and then we plug in our c value. So it's 1 minus 1 over pi. Okay, and that would be the solution to this initial value problem. Okay, so yeah, the procedure is pretty straightforward, and it turns out you can repeat this. So here, this is a slightly different type of problem. Here I'm given that the second derivative is something. And now I'm given two informations. I'm given a point on the original graph, and then also a point on the derivative graph. And it turns out, given all this, it turns out you can find what r itself was. And you basically do the same procedure we did twice. Okay, so each time we're undoing one derivative, right? That's sort of the idea behind all this. So our first step would be to find, we would undo one derivative, just go from the second derivative to the first derivative. So that would be finding the antiderivative of the second derivative should be the first derivative. And that'll be, we increase the power by 1. And so we would get like this. And now, because we have a function where we have the first derivative in there, the only piece of information that would make sense to use is this second one that tells us stuff about the first derivative. So if we plug that in, it would say r prime of 0, that better be 3. And so that means we're plugging in t equals 0. So that'll be 0 plus 0 plus c. So this just says 3 is c. Okay, and now that tells us exactly what the derivative was. It's t squared over 2 plus t plus 3. Okay, because our goal is to find r. So now we repeat the procedure. Now we undo one more derivative by taking the antiderivative again. So you increase the exponent by 1, and you'll get 2 times 3 now. And you get another constant. So it'd probably be best if you call it by a different name, maybe d instead of c. Because d and c aren't going to be the same number, so it's good to give them different names when they're different things. And then you would use the second piece of information. Now we use this other piece that's telling us about the r with no derivatives. So what did that say? R of 0 is 2. So r of 0 is 2. Means we're plugging t equals 0 in. We just get a bunch of zeros. So this says 2 is d. And then we throw that in here, and that's our final answer. So r of t is 1/6 t cubed plus 2. Okay. Alrighty, so any questions about that? All right, so that's it for section 3.9. Because we have a little bit of extra time, I'm going to go through one more optimization example from what we were doing on Wednesday. This one's kind of a curious little one. So this question is kind of motivated, like if you're moving furniture and you have like a big couch or something and you're trying to move it around a corner, what's the longest couch you could actually move around the corner? But I made it a steel pipe so it's easier to visualize. So what we're asking here is, the basic idea is, make it a little bit smaller. So the basic idea is if you have a hallway that makes a right angle corner, right, and then you have a long steel pipe that you're only allowed to carry perfectly horizontally, just to make the problem simple. And we know that the hallway is 9 feet wide. So like we have this pipe, let's maybe make that a different color. I don't know what a good color for pipes are. So you have a long steel pipe, right? And you're going to try to move it around this corner, right? So you might start out carrying it like this, and then you move it around the corner. But if you make it too long, it's not going to fit around the corner, right? If you had a really long one, let's not do that. If you had a really long one, you might get it stuck, right? If you had a pipe like this long, it's going to start touching both the walls, and that's going to be an issue, right? And so the question is, how long of a pipe will actually make it around this corner? And there's sort of two ways you could approach this. You could think of this as either a maximization problem or a minimization problem. So the way it's phrased, you might first think that you would do a maximization problem because it's asking for the longest. But it turns out it's easier to do this as a minimization problem. And so what we're gonna, so the way we would think about it as a minimization problem is we're gonna imagine like we start with a super long pipe, right? And as we start trying to move it around the corner, at some point it's going to start hitting the walls, right? So just like before, you might have it start hitting the walls. And that means your pipe's too long. So then we would shorten the pipe, maybe make the pipe a little shorter, and now it'll fit a little bit more in, right? It'll go around the corner a little farther. Then you make it a little smaller. Maybe you make it a little smaller, and it turns out it actually starts fitting through the pipe. So we're kind of decreasing the length of the pipe, and we're asking, when will it actually make it around the corner? So the idea here is, so let me complete the picture. Let's see. Oh God. We're just going to have to leave those blue dots. So for each length of pipe, there's going to be sort of a place that it touches both walls, right? And if you wanted to make it around the corner all the way, it has to pass through all angles. And so we're asking, as you move this pipe inward, what's the shortest length of all these blue lines, right? Because that's the one that it has to, the smallest, like the worst place. It's a little hard to describe, not in person. Oh God. So basically we're asking like, oh, it's still the eraser, for which angle is this length the shortest? Because the shortest length is the worst place in the corner, like the worst angle that it has to go through. And so that's one way you can think of it as a minimization problem. And so then what you would do is you would draw like little triangles here. So let's not make that blue. So we want to figure out what angle makes this blue line the shortest, because that will be exactly the length of the longest pipe that makes it all the way through. And so we're going to call the length of this entire blue line L. So the length of the pipe is L. And the other thing that varies, that changes as we move around the corner, we can think of that as changing the angle here. So that'll be the same as this angle here. And if you think about this triangle, we do know some sides of these little triangles. Like we know this side is 9, we know this side is 9. And to make our lives a little easier, I'm going to call these smaller lengths like L1 and L2, right, where they just go halfway from like here to here. Okay, and so the thing we're trying to minimize is the length of this, so we have to write down an equation for the length. So the length is going to be just L1 plus L2, but we're going to write these in terms of the angles. So if you think about L1 and you write down the triangle, maybe it's best if I say it like sine of theta is opposite, which is 9, over hypotenuse, which is L1. And if you do cosine of the other triangle, so if you do this other triangle here, then if you do cosine in that triangle, that would be adjacent, which is 9 over L2. So this will tell you that L1 is really sine theta over 9. Sorry, 9 over sine theta. This one tells you that L2 is 9 over cosine theta. So you can throw these into an equation where now you just have one variable. Okay. And then you try to apply your usual optimization technique. You take the derivative. And here it might be worth realizing that this is really 9 cosecant, and this is really 9 secant. So the derivative of cosecant, remember, is cosecant cotangent And the derivative of secant is secant tangent, secant theta tan theta. Okay. And we're trying to figure out where that derivative is 0. So maybe we do a little rearranging. So let's move this term to the other side. So we don't need the plus. And let's write everything in terms of sines and cosines. So sine is 1 over, or secant is 1 over cosine. Cosecant is 1 over sine. Cotangent is cosine over sine. And then let's try to get everything on one side. So we can cancel the 9s out. And I'm going to move the and then I'm going to basically move all the trig functions over here. So that means I'm going to get an extra 2 sines on the top. So I'm going to get a sine cubed on top. I'm going to divide by the cosine. So on the bottom, there's going to be 3 cosines. And I'm just going to be left with a 1. So if you think about this, this just really says that tan cubed theta has to be 1. And if you think about it, the only angle, so if you cube root things, you get that the tangent theta has to be 1, and the only angle that makes that work that's in between 0 and 90 is pi over 4. Okay. And it turns out that that's the correct answer. And so what you would do is you'd go back and plug that in here. So and I'll save you the work and just tell you that it works out to be 18 root 2, I believe, feet. Alrighty, so I just wanted to give you an example of something that was a little bit different for applied optimization. But that'll be it for today. Hope you guys all have a great weekend, and I'll see you on Monday.